Hey everybody, welcome back. We're on chapter 10, part 2. So we're talking again about regression. And in this lecture, we're mostly going to be doing some practice problems as well as introducing a new concept or two. So let's dive in. All right, let's start with some practice. So how many variables are used in simple linear regression, which is the kind of regression we've been doing so far? There are two variables, right? You've got a predictor variable, which is your x variable. You've got an outcome variable, which is your y variable. And you're trying to predict values of the outcome based on values of your x variable, your predictor variable. Now, those two variables have to be on what kind of measurement scale? They have to be numeric. They've got to be numeric. So you can't use categorical data when you're using linear regression. So you can't use, certainly not nominal stuff, and you wouldn't use ordinal data either. Now you might be thinking, well, okay, correlations also use two numeric variables. So what's the difference? What's the difference between correlation and linear regression? Well, both of them are attempting to describe a linear relationship between two variables. So that's what they have in common. But what's different is correlations are just, they give you the strength and direction of the general relationship between the two variables. Whereas in linear regression, you're actually trying to predict values of the outcome based on your independent variable, your x variable, which is also called the predictor variable. So in correlations, the sort of the direction of does, the x variable influence the y variable or the y variable influence the x variable, you don't know and you don't really care. In linear regression, you do care because your predictor variable is then predicting the outcome variable. And so the directionality actually definitely matters. We'll talk more about that over the course of the semester. But anyways, those are kind of the general similarities and differences between correlation and regression. All right, so let's get into it. Today we're going to be predicting hours of sleep from cups of coffee consumed. Okay, and you might think about just in general, what kind of relationship would you expect to see? Would you expect to see a positive relationship where the more cups of coffee somebody consumes, the more sleep they get? Or would you maybe see a negative relationship where the more cups of coffee you consume, the less hours of sleep you get? Yeah, you'd expect this to be a negative relationship, right? As cups of coffee increases, we'd probably expect to see less sleep, which in a regression is going to be indicated by a negative slope. That means the higher value on x, the lower value on y, or at least in terms of slope and interpreting the slope, it's for every 1 unit increase in x, which would be 1 cup of coffee, what happens to sleep? And it'll probably, we'll find, I'm going to guess, that sleep in hours decreases by a bit. How much? Well, we're going to find that out. Let's calculate it. First, of course, we're going to have to calculate the covariance on our way to being able to calculate the slope. So again, what we're up to here is trying to find the equation for the line of best fit that goes through as many points as possible between coffee and sleep on a scatter plot. And in order to find the equation for that line, which is the regression line essentially, we've got to first start with covariance. So go ahead and do that for me. What is the covariance between cups of coffee and hours of sleep? Okay, so where do we start? Remember, you have to first, you're going to calculate the mean for x and y. So the mean cups of coffee, the mean hours of sleep for this sample. Then you're going to have to get the deviations of x and y for each participant. So you take all of the raw scores for x, the cups of coffee, you subtract the mean cups of coffee from that for each person. That's your deviation of coffee column. You have a deviation of sleep column, which again, for each participant, you take their raw score, the number of hours they slept last night, You subtract the mean number of hours people slept from that. You get your deviation for sleep column. And then you have to make a new column that's deviation of products, or I'm sorry, the products of the deviations. That's right. So you have to multiply the deviation scores on X times the deviation scores on Y for each participant. That gives you this deviation products column. And then you have to add all of those deviation products up. Okay, you add them all up. And here we found a deviation, the sum of all the deviation products was negative 19. Then you have to divide that. The denominator of the covariance equation is n minus 1. So we're going to divide what we just found, negative 19, by n minus 1. There's 7 people, so n minus 1 is 6. So you take negative 19 and divide it by 6, and you end up with a covariance of negative 3.166666, which we're going to round to negative 3.17. All right, now you know what's coming next. We got to calculate the slope so that we can ultimately, we're working towards getting our equation for our line of best fit, right? So we need the slope, and then we can eventually work towards the y-intercept, and then we'll have all the pieces necessary to start answering the original question. So the slope is equal to the covariance that we just found divided by the variance of cups of coffee, the variance of our x variable. Remember that variance is just standard deviation squared, right? So go ahead and do that and let me know, what value did you get for the slope? So what you need to do is first find the variance for cups of coffee, the variance for our x variable. So I did that in Excel, and it's over there on the bottom left there, variance of 2.33333. Then all you have to do is take the covariance that we've already found to be negative 3.17, divide it by the variance, and you get your slope. And our slope is negative 1.36. And isn't that interesting? We had thought that this probably would be a negative relationship, where the more cups of coffee you drink, the less sleep you probably get, right? And this slope, the interpretation of this slope, follow me here, this is important to know because you'll definitely be tested on it. For every 1 unit increase in your x variable, this is how the y variable changes. So for every increase in cups of coffee, meaning for every additional cup of coffee you would drink, at least based on this sample data, we would expect that you would sleep 1.36 hours less, right? For every additional cup of coffee you drink, we would expect, because this is all predictions, we don't actually know, but it's all predictions based on the data, we would expect for every 1 cup of coffee additional that you drink, you would sleep 1.36 hours less. All right, now all we have to do is use the numbers we've already calculated to find the y-intercept, which is denoted as A. So we're going to find that the y-intercept equals the mean of our y variable, the mean hours of sleep, minus our slope times the mean cups of coffee. And we've already done that, or at least we've already got all the numbers, so all you got to do is plug them in. So what is the y-intercept for the line of best fit for these two variables? So we take our average number of hours of sleep, which was 7.14, and we subtract from that the product of our slope, negative 1.36, times the mean of x, which was 2 cups of coffee. And so you're actually subtracting a negative number here, which means you're actually going to add a positive. So you ultimately end up with a y-intercept of 9.86. Now, what does that number mean? The y-intercept, remember, is it's the value of y, it's the value of hours of sleep when x equals 0, when cups of coffee equals 0. So in plain English, the expected number of hours of sleep somebody would get when they've had 0 cups of coffee is 9.86 hours of sleep. All right, nice. Now we've got our equation for the line of best fit through these data. That is our regression line, and it says that y hat, the predicted value of y, is going to equal negative 1.36, that's our slope, times x plus 9.86. Now remember, we are trying to predict how many hours of sleep somebody should get or would get if they've had 8 cups of coffee. So go ahead and find that out for me and type it in. Well, this is pretty hilarious. You end up with a negative value, indicating that somebody who drinks 8 cups of coffee would actually sleep negative 1.02 hours, meaning they don't sleep at all. So, of course, that's kind of a ridiculous answer, although it's very fun to think about. So let's try 5 cups of coffee. For the next question that I have for you, how much sleep would we expect somebody to get if they've had 5 cups of coffee? If you do the math, you get 3.06 hours of sleep. So we would expect, based on these data, if somebody had 5 cups of coffee, that they would only sleep 3.06 hours. Now remember, nobody in our sample actually drank 5 cups of coffee. I think the highest was 4 cups of coffee. So this is nice because it allows you to just think about and predict, well, even though in our sample we didn't see some kind of specific thing happen, we could still predict what the outcome would be, even if we don't objectively have that information on hand. That's why regression can be really powerful. Now, note that, the regression line that we calculated and these predictions that we're making right now, these are all just based on the specific sample that we have. This doesn't mean that, like, for everyone in every situation and all different populations and groups of people, that if you drink 5 cups of coffee, you'll only sleep 3.06 hours. This is all just based on our specific sample, and this is just a prediction. So even if somebody in our specific sample drank 5 cups of coffee, we don't know that they would sleep exactly 3.06 hours, but it is a useful way to predict those kinds of things. So you can use Excel like I've done here, or you could certainly use R if you wanted to create a scatter plot that also shows the trend line, the line of best fit that we just calculated. And as you can see, right, that line is going from the top left to the bottom right, meaning this is a negative slope, and therefore there's a negative relationship between cups of coffee and sleep, such that as you drink more cups of coffee, you get less sleep. But remember that this trend line is our prediction line, right? But like I was mentioning, well, the line of best fit is as good as we can get when it comes to creating a straight line through a bunch of different observations or a bunch of different dots. But it's never going to be perfect because not every single dot will lie exactly along that line of best fit unless you had a perfect 1.0 or negative 1.0 correlation. Then every single dot lies exactly along the line of best fit. That almost never happens in practice. And so we have some amount of error in our line of best fit. And so there's a statistic called an R-squared statistic, which tells you basically how good is this estimate that we're using, this line that we're using to predict future observations. Another way of defining this R-squared statistic is saying it's a measure of how much variability in the outcome measure is explained by changes in the independent measure. So again, if it's a really high amount of variability is explained, that means that your X and Y variables tend to go together very strongly. So like when we saw like height and weight, those things are pretty highly correlated. They're not perfectly highly correlated because there are some people who are shorter and weigh more and some people who are taller and weigh less. But on average, taller people weigh more and shorter people weigh less, right? And so it would be a very high R squared. More of those dots would fall closer to the line of best fit. Hopefully that makes some sense. Now, a fun thing about the R squared statistic is that if you already know the Pearson R correlation coefficient, which is literally R, all you have to do is square that value and you get this R squared fit statistic. That only works if you're using only one variable as a predictor, one independent variable, which we'll talk about more in a second. So earlier we found a correlation R 0.93 when we were talking about number of hours studied and the final exam grade. If you square 0.93, you get 0.86, and that tells you that 86% of the variability of final exam scores is explained by the number of hours that students study for the exam. That's a lot. That's a lot. That means that your final exam score is predicted very highly by the amount of hours that you study. Well, what about the last 14%? You know, this is 86%, 14% would get you up to 100% explanation of the variability of final exam scores. Well, that last 14% could be a ton of different things, right? It could be, well, what mood are you in when you take the exam? Well, how cold or how warm is it? Do you have to go to the bathroom or not, right? Like, have you had any food recently? There's all kinds of different things that might predict to a small extent the variability in that final exam score, but the vast majority of it is covered by how much you actually study. So in our example that we just went over, you could calculate the correlation coefficient. It would be negative 0.71, which we would also expect there to be a negative relationship, just like we saw with the negative slope, right? But this is just sort of a general overall relationship between cups of coffee and sleep, and we're not using R to predict anything specifically. But if you square that correlation coefficient, you get R squared, which is a fit statistic for the line of best fit between these two variables, right? And so what you find is an R squared of 0.50 after you round. That means that 50% of the variability in hours of sleep is accounted for by the number of cups of coffee that these participants drank. That's a lot. That means that half of the variability in your sleep is dictated by how much coffee you drink. That's a lot, meaning that coffee accounts for half of the amount of sleep you get. That makes a lot of sense, and it's a lot. Now again, this is all made up data, and this only applies to these specific people in this specific sample. Because of course, when you think about it, like, well, it's not just that coffee affects your sleep. There's all kinds of things that can affect your sleep. Going out, workload, stress, your health, all that good stuff. And that would account for the other 50%. Now in the real world, like all those other things probably actually account for much more than 50% of the variability. And coffee drinking will account for some of the variability, but I made these data up, so you never know. In the real world, maybe coffee drinking accounts for 10% or something like that of people's hours of sleep, whereas other variables affect it much more. I'm not sure, but it might be something worth looking into. Anyways, hopefully that was interesting. Thanks very much. You did it. You made it to the end. I know that was a lot of stuff. I really like this meme because, of course, on a scatter plot, which these little blue circles represent individual participant observations on two different variables, you'll have what their actual scores were, and then you'll have the line of best fit, right? But the problem is there's always going to be some error because the line of best fit doesn't always exactly go through every single point on the scatter plot, unless, again, it's like a perfect 1.0 or negative 1.0 correlation. So I like this because, Michael Caine is saying, you trusted me and I failed you. This would be like an example of
If you wanted to guess how well you did on the exam from how many hours you studied, and you studied 4 hours, but you got a worse score on the exam than what was predicted by the regression line, well, you'd be a little miffed by that, I would assume. But it can happen, right? Because there's always going to be some error.
So that's it for this week. See you in the next video.